In the previous slides, we saw that the spins in the flowing rod do not produce the echo signal at all the echo processes. This was because the phase change of the spins in the flowing rod depend on the square of time. On the other hand, the phase change of the spins in the stationary tissues depend only on the time. Due to this difference, the spins in the flowing rod do not produce the MR signal at all echo processes, while the spins in the stationary tissues produce the MR signal at both odd and even echo processes. You can resolve this odd echo defacing of the spins in the flowing rod by using the flow compensation gradient. The flowing compensation gradient consists of two gradients with the same area but opposite direction. Okay. The two gradient fields constituting the flow compensation gradient are opposite in direction but have the same area as gradient for frequency encoding gradient. So flow compensation gradient is applied along the x-axis. So x-axis is the frequency encoding gradient, and this flow compensation gradient consists of two gradients with the same area but opposite directions. The gradients with slopes of g plus g and minus g are successively applied here. The gradient's time duration is tau. In this case, t equals 6 tau, since 3 tau corresponds to t over 2. So the time interval between 90° pulse and 180° pulse is t over 2. And time interval between 180° pulse and echo signal is also t over 2. So we divided t over 2 into 3 regions. So each region corresponds to the time tau. Okay, so t over 2 corresponds to 3 tau. Due to the first minus g gradient, this gradient, the phase changes to minus k tau square at time tau. So using this relation, here we have now gx equal minus g. So the phase change at this point, at this moment, minus g is minus g. So minus 2 kt integral from 0 to tau from here to here. So we can have phase change in minus k tau square at this moment tau, right? Okay, now the second plus g gradient causes the phase to 2k taus at time over 2 tau. Okay, this moment, so starting from minus k tau square here, and this plus g, so 2kt, and from tau to 2 tau, so you can have phase change 2k tau square at t equal 2 tau. Okay. Between these two points, there is no gradient, so phase does not change. Okay. And at this moment, 180-degree pulse is applied. So by the 180-degree pulse at 3 tau, the phase changes to negative, minus 2k tau square. So here 2k tau square, but due to the 180-degree pulse, phase becomes negative. Okay, so minus 2k tau square. At this moment, frequency encoding gradient is applied. The frequency encoding gradient at 4 tau, so at this moment, okay, as minus g, slope of minus g is applied at this moment at 4 tau. So due to this gradient, we can calculate the phase change at this moment, starting from minus 2k tau square, yeah, and time is from 4 tau to 5 tau, and minus g, so minus 2 kt dt. So we can have minus 11k tau square at this moment. Okay. So we have phase change to minus 11k tau square. The echo signal is produced as a result of zero phase at time 6 tau. So at this moment, if we calculate the phase change starting from minus 11k tau square, and time is from 5 tau to 6 tau, so this plus g, so 2 kt, so we have 0. So at this moment, the phase of the spins in the flowing rod become 0. So we can have the echo signal. Okay. So as a result, by adding flow compensation gradient to the spin echo pulse sequence, we are able to obtain the echo signal at the first order spin echo per sequence process. The spins in the stationary tissues are not affected by this compensation, pro-compensation gradient, because minus G is just linearly decreasing, phase is linearly decreasing, and for plus G also phase is linearly increasing. So this phase pro-compensation gradient the spins in the stationary tissues, the phase is 0 here, and after this flow compensation gradient still 0. So there's no effect of this flow compensation gradient on the spins in the stationary tissues. Okay. Now let's see the flow compensation gradient applied to the GRE for sequence. The phase changes to k tau square at t at tau due to the first plus g of the flow compensation gradient. So here, starting from 0 phase, due to this plus g gradient, the phase change at this moment can be calculated. Using this relation, we can get k tau square here. Okay. The second, minus g of the flow compensation gradient shifts the phase to minus 5k tau square at 2 tau. So at this moment, the phase is changing from k tau square, okay, and tau is tau to 2 tau, and here this is for flow compensation gradient, and this one is frequency encoding gradient. So these two gradients are added, so we have minus 2g slope of the gradient. Therefore, in this relation, here 4k and minus 2g, so minus 4k. Okay. And we can get minus 5k tau square phase change here. And the phase change is to 0 at the frequency encoding gradient center, producing the echo signal. So the at center of the frequency encoding gradient at this moment, if we calculate the phase change, starting from minus 5k tau square, time is from 2 tau to 3 tau, and we have plus g, so this 2k, and then we finally have the 0 phase, so we can get echo signal at this moment at center of the frequency encoding gradient. The spins in the stationary tissues, phase change is linear, that's plus G. So change in this way, and this is minus 2G. So this way, and plus G. So this linear change. So the spins in the stationary tissue also produce the echo signal because the phase is 0 at this moment. So we are able to capture the echo signal at the first order GRE per sequence. So we resolved the echo dephasing problem using this flow compensation gradient. The spins in stationary tissues produce echo signals at both the even and odd GRE per sequence of processes because they are unaffected by the plus G and minus G of the FC gradient. You can see here there's no change of phase because one is plus G and the other is minus G. So for stationary tissues, the spins in the stationary tissues, phase is not affected by this flow compensation gradient. So we could resolve the odd echo dephasing problem using flow compensation gradient in spinnacle per sequence and also GRE per sequence. These slides show the sequence of TOF MRA. This MRA gives a bright blood MRA. The FRE flow-related enhancement effects in the GRE per sequence are used in TOF MRA. The MR signals from the spins and the flowing blood are much larger than those from the spins in the stationary tissue because of the TOF effects. We already discussed this before. Moreover, the GRE per sequence's TE time is very short, which reduces the to-star dephasing and flow-related signal loss. The consequence is well-contrasted MR images where the blood is significantly brighter than the stationary tissues. GRE-based per sequences are widely applied in MRA. In this sequence, we can see flow compensation gradient here to resolve the problem of the odd echo dephasing. And here the phase rewind is used, exploring the remaining transverse normalization. This will not be discussed here. Now let's see the flow encoding for the phase contrast MRA. we can determine the velocity of the flowing rod by using flow encoding a bipolar gradient. The flow encoding bipolar gradient consists of two gradients with the same area but opposite direction. So the same area, but this is plus and this is minus. Okay. The flow encoding bipolar gradient enables us to determine both velocity of the rod and the direction of the flowing rod. This technique is used in phase contrast MRA. As was previously discussed, the spins in rod that are moving at the velocity v undergoes phase change of deceleration in the gradient field Gx. Hence, the velocity of the spins at the particular location can be calculated once the phase phi there is determined. So, if we determine the phase at the specific position, then we can calculate the velocity of the flowing rod at that site. The flow encoding gradient with bipolar gradient structure is employed in the phase contrast MRA to obtain the spin velocities at various positions. Two gradient fields with same area and opposite directions make up the flow encoding gradient. Hence, the flowing encoding gradient does not result in the phase change of the spins in the stationary tissue. Yet, the flowing encoding gradient causes the spins in the flowing rod to experience a velocity-dependent phase change. You can see here, before the flow encoding a bipolar gradient, phase is 0, both for the spins in the flowing rod and the stationary tissues. This is plus gradient. So the phase change at this moment for the spins in the flowing rod can be calculated to be k tau square. So the phase change here for the spins in the flowing rod is k tau square. On the other hand, for the spins in the stationary tissue, the phase change is linear, depends on just time t, so you can see the linear increase of phase due to this plus gradient. And now we have minus gradient flow encoding gradient. Then at this moment we can calculate phase change for the spins in the flowing rod starting from k tau square here and the time is from tau to tau, and minus 2kt. So we can have the phase change minus 2k tau square at this moment. However, for the stationary tissue, the spins in the stationary tissues, phase change due to this minus gradient is also linear. So at this moment, phase will become 0 because the area of this gradient are the same. So the same effect, plus effect and minus effect. So we can have 0 phase here. So this means that the spins in the stationary tissues are not affected by this bipolar gradient. So no phase change due to this bipolar gradient. On the other hand, for the spins in the moving flowing blood, the phase will change to minus k, 2k tau square. So there is some net phase difference between the spins in the flowing blood and the stationary tissues. Okay. The PC-MRA, the phase contrast MRA, can thus discriminate between stationary tissues and blood. Both the phase map for the blood's flowing direction and the image of the blood can be generated with PC-MRA. The phase map can show the direction of blood flow. So in the PC phase contrast MRA, we can obtain informations about the velocity of the flowing blood, and also we can have the information about the direction of the flowing blood. This slide shows the sequence of the phase contrast MRA. This gives the bright blood MRA. This sequence shows the example of the 3D PC-MRA using GRE for sequence. Here we use the flow encoding bipolar gradient, and also we use the flow compensation gradient to resolve the odd echo of the phasing problem. The FE and FC gradients are used respectively for flow encoding and the flow compensation. We can determine the blood flow's velocity and the direction using the phase contrast MRA's magnitude and the phase images respectively. So from the magnitude image, we can obtain the velocity of the flowing blood, and from the phase images we can get the information of direction of the flowing blood. Okay. This slide shows why we have bright image for blood in the GRE per sequence. Every slice in the entry slice in the GRE per sequence. So FRE effect applies to every slice and the volume. So we have a bright image for the flowing blood. Next, no refocusing 180-degree pulse. So TOF process does not occur. And also, even if the TOF effect exists, they are very small, not significant. Next, TE is very short, which minimizes the signal loss caused by defacing. So due to these three reasons, we can have bright images in the bright images of the flowing blood in the GRE pulse sequence. Next, we will see the method for obtaining the dark blood image, dark blood MRA. We use the double inversion recovery for dark blood MRA imaging. To obtain the dark blood MRA image, we use the double inversion recovery pulse sequence. In this pulse sequence, we used 2 consecutive 180-degree pulses. The spins in the stationary tissues are not affected by these 2 180-degree pulses. The direction of longitudinal modulation of the spins and the stationary tissues is reversed by the first 180-degree pulse. However, the modulation recovers its original direction by the second 180-degree pulse. So due to first 180-degree pulse, the direction of the modulation of these spins in the stationary tissues is reversed, but the second 100-degree pulses reverse the longitudinal modulation direction to its original direction. Thus, the spins and the stationary tissues are not affected by these 2 180-degree pulses. However, the directions of modulation of the spins in the incoming blood into the image thickness is reversed by the second 180-degree pulse. After this 180-degree pulse, the reversed longitudinal modulation recovers and pass through the 0 point. Okay. If we match the time of inversion to the null point of the flowing blood spins, we can eliminate the signal from the spins in the flowing blood. In this way, the signals from the flowing blood are eliminated, while the signals from the stationary tissues are not changed. Consequently, we can get dark blood MRA imaging because the spins in the flowing blood do not produce the signal, so the blood vessel appears dark, and the surrounding tissues, stationary tissues, their intensity is not changed by this to 180 degree pulses. Okay, let's see again here. The single inversion recovery pulse sequence is used for getting the dark blood MRA. We can use that. However, in this case, the inversion time is set to the max relaxation time of the spins in the flowing blood. So in this case, it has the disadvantage of possibly reducing the signal from spins in the stationary tissues whose T1 is similar to that of the spins in the flowing blood. So, in the single inversion recovery pulse sequence, we use the time of inversion as relaxation time, T1 relaxation time, at the null point of the flowing blood. But some stationary tissues may have the nearly same null point of the as the that of the flowing blood. So the signal from the stationary tissues can be reduced by this characteristic. This problem can be solved by using double immersion recovery pulse sequence. So the DIR, double immersion recovery, is used to get all this disadvantage. Two 180 degree pulses are successively applied to the spins and the DIR. For example, when getting the MRA of the heart, the first 180 degree pulse is applied to the entire chest. So the first 180 degree pulse is non-selective pulse. Right? So this 180 pulse is not applied to specific slice, but some reason, including the organ you want to visualize. So, for example, if you want to have the heart image, then this non-selective 180 degree pulse is applied the entire chest. So this entire chest includes the heart, right? We want to make a heart image. So in this case, first 180 degree pulse is not applied to some specific slide of the heart, but applied to an entire region including heart. Okay, so this is non-selective pulse. Then the longitudinal modulation direction of the spins close to the heart is then reversed by this non-selective pulse. So the spins near the heart, the longitudinal modulation direction is changed by this non-selective 180-degree pulse. Okay. So this shows this arrow or indicates the longitudinal modulation of the stationary tissue. Okay, this reversed by this 180-degree pulse. Okay, the second 180-degree pulse is applied to the selective slice immediately after the first 180-degree pulse. The second 180-degree pulse is slice selective pulse. So this pulse is applied to the specific slice we want to make the image, the heart, right? So the second 180 pulse is applied to selective slice immediately after the first 180 pulse. So in this figure there's some interval, but this is immediately applied. Okay. Then the spins longitudinal modulation in the stationary tissues then returns to almost its original value, because the second 180-degree pulse is applied immediately after the first 180-degree pulse. So the longitudinal modulation of the spins in the stationary tissues reverse its direction to the original orientation, and also the magnitude of the longitudinal modulation is the nearly same before the first 180-degree pulse is applied. Okay. So the spins longitudinal modulation in the stationary tissues then returns to its initial value before the first 180-degree pulse is applied. On the other hand, the second 180-degree pulse reverses the direction of the longitudinal modulation of the blood spins that entered the slice after the first 180-degree pulse. So blood is flowing into the image thickness. So the modulation of the spins of flowing blood into the image thickness is reversed by this second 180-degree pulse. So this shows the as red arrow. Okay. So the second 180-degree pulse reverses direction of the longitudinal modulation of blood spins that enter the slice after the first 180-degree pulse. So this is reversed. Okay. This longitudinal normalization then recovers, right? Just recovers, and this is negative minus normalization, so it's recovering to its original value, but in this case, this normalization must pass through the 0 point. Okay, it's recovering, so this way is recovered, but it passed the 0 point, and it's recovered. Okay, so its longitudinal normalization recovers and passes through 0 normalization after the second 180 pulse. So should pass this 0 point. If the fast spin pulse sequence starts here, from here, when mg equals 0, this means selecting this time as time of inversion, Ti. We choose this, the starting point of the fast spin echo or pulse sequence. Then the MR signals from the blood flowing slice spins are 0, so eliminated, right? So no signal is produced by the flowing blood, so resulting in the dark blood MRA. So in this way, we can obtain dark blood MRA. In the single inversion recovery pulse sequence, the signal from the spins from stationary tissues could be reduced. We already discussed this. However, double inversion recovery pulse sequence can only eliminate the signal from the spins in the flowing blood. Okay? The signal from the stationary tissues is unaffected. Moreover, the third 180-degree pulse may be applied, and this third 180-degree pulse is employed to suppress the signal from the fat, which is so-called fat suppression. This is referred to as TIR, triple inversion recovery, which is widely used in the dark blood MRA. You can see TIR image and TIR image, and the T1 image, TIR, and T2 TIR images. This slide summarizes the MRA types. There are two types of MRA, dark blood MRA and bright blood MRA. In the dark blood MRA, we use the fast spin echo or inversion recovery or susceptibility weighted. And for bright blood MRA, there are two types, non-contrast and contrast enhanced. Non-contrast, we don't use any contrast agents, but in the contrast enhanced MRA, we use the gadolinium based agents. So there are several characteristics for the non-contrast MRAs here. Now let's see the basic principle of functional MRA. Functional MRI. MRI is used for brain mapping in functional MRI. We call this fMRI. To supply oxygen to brain tissues, hemoglobin in the blood exists in the form of oxyhemoglobin. Okay? After delivering oxygen to the brain tissues, oxyhemoglobin converts to deoxyhemoglobin. So this oxyhemoglobin contains the oxygen, and the oxyhemoglobin oxygen is used to the tissue, so there's no oxygen. As a result, the blood has a certain ratio of oxyhemoglobin to the deoxyhemoglobin. If a certain part of the brain is activated, it requires extra oxygen. As a result, the amount of oxyhemoglobin in that part of the brain increases. Because of its unpaired electrons, deoxyhemoglobin is paramagnetic, whereas oxyhemoglobin is antimagnetic. So deoxyhemoglobin is paramagnetic. So it influences the relaxation, right? So the phasing of nuclear spin is accelerated by paramagnetic deoxyhemoglobin, which reduces the MR signals in the T2 weighted images. So deoxyhemoglobin is paramagnetic, so it accelerates the relaxation process. So T2 relaxation process, then that results in the reduction of the MR signals. Right? If compared to the non-active part of the brain, the amount of deoxyhemoglobin in the active region is less. In the active region, we need more oxyhemoglobin. So, in the active region, the amount of oxyhemoglobin is less. Okay. As a result, the active region's MR signal is large, and the active region appears brighter in the MR image. In the active region, there are less deoxyhemoglobin. Deoxyhemoglobin reduces the MR signals in the T2 weighted images, but the active region contains less deoxyhemoglobin, so the active region appears brighter because the signal reduction is due to the deoxyhemoglobin, so active region has less deoxyhemoglobin, so the signal reduction in the active region is less. So consequently, active region appears brighter in the MR image. At the field of 1.5 Tesla, the maximum change in the ratio of oxyhemoglobin to deoxyhemoglobin is roughly 6%. This difference, however, is sufficient to distinguish active from non-active regions. We can obtain brain mapping in this way, which shows which part of the brain is related to a specific action or stimulus. So let's summarize again. the active regions of the brain need more oxyhemoglobin. Thus, the amount of deoxyhemoglobin in the active region is less. Deoxyhemoglobin enhances the T2 relaxation process and reduces the MRA signal in the T2 weighted imaging. Since the amount of deoxyhemoglobin in the active region is less, the signal reduction effect is also less. Consequently, the active region appears brighter than the non-active region in the T2 weighted imaging. Okay.